2004, a magnetar on the far side of the galaxy released a burst of energy that physically compressed Earth's ionosphere from 40,000 light years away. Scientists detected it with instruments designed to survive nuclear war, and those instruments nearly maxed out. That was a relatively weak magnetar at a relatively safe distance. Today, we are going to rank the places in the universe where that event would be considered mild, ordinary, and completely unremarkable on the scale of local hazards. The universe is not a quiet, empty void waiting to be explored at leisure by curious civilizations. It is layered with zones of escalating violence, each one operating on energy scales that make nuclear weapons look like struck matches. What we are building here is a hierarchy of cosmic danger, from the merely lethal to the genuinely incomprehensible. By the end, the 2004 Magnetire event will feel less like a warning shot and more like a gentle reminder that we live inside something that does not care whether we survive. Not every threat in the universe looks the same, and that makes ranking them genuinely complicated for scientists. Some environments kill through raw heat, pushing temperatures far beyond anything matter can survive intact. Others destroy through radiation, flooding space with energy that tears apart molecules at the atomic level. Then there are gravitational forces so extreme they stretch matter into threads before it vanishes entirely. Scientists use a loose but powerful framework when comparing these environments across cosmic scales. They ask how quickly a threat could deliver a lethal dose of energy to an unprotected human body. They ask whether the danger is local or whether it reaches across light years of open space. And they ask whether anything, any shielding, any distance, any physics we know could offer meaningful protection. When you apply that framework consistently, a clear hierarchy starts to emerge from the data. The universe doesn't just have one most dangerous place. It has layers of danger, each one more extreme than the last. Star-forming regions look almost peaceful in photographs. Vast clouds of gas and dust glowing softly against the dark. But that beauty is deeply misleading because inside those clouds, creation and destruction are happening at the exact same time. Newborn stars ignite with almost no warning, and when they do, they release enormous bursts of ultraviolet radiation that tear surrounding gas apart at the molecular level. Shockwaves from stellar winds slam outward at hundreds of kilometers per second, compressing nearby material until it too collapses and ignites. The violence compounds on itself in a chain reaction that reshapes entire regions of space. Any planet unlucky enough to form too close to one of these ignition points would be stripped of its atmosphere before life ever had a chance to begin. These nurseries are not gentle birthplaces. They are pressure cookers running at cosmic scale where the energy required to build something new also has the power to erase everything around it. Scale up from a stellar nursery and you arrive at something even more extreme. The surface of a hypergiant star. Eta Carinae is one of the most massive stars we know of, burning at roughly 5 million times the luminosity of our sun. The radiation pressure alone would tear a human body apart before you even got close to the surface. We're talking about a star so unstable it periodically erupts, hurling entire shells of gas into space at thousands of kilometers per second. The temperature at its surface hovers around 40,000 degrees Kelvin, hot enough to ionize everything in its immediate neighborhood. Ultraviolet radiation floods outward in quantities that would strip the atmosphere from any nearby planet within geological eye blinks. Even at the distance of Earth from our own sun, the energy output would be catastrophic and immediate. Nothing we know of could survive proximity to a star like this. Not rock, not metal, not any chemistry that produces life. When a massive star exhausts its fuel, the core collapses in less than a single second. What follows releases more energy than our sun will produce across its entire 10 billion year lifetime. That energy doesn't just radiate outward, it detonates outward in every direction at once. The shockwave alone can vaporize anything within a few light years almost instantaneously. But the real killer isn't the heat or the blast, it's the neutrino flood. The real killer isn't the heat or the blast, it's the neutrino flood. At close range, that neutrino burst delivers a lethal radiation dose before you could register anything was wrong. Scientists estimate that any planet within about 50 light years faces catastrophic damage to its atmosphere and biosphere. Beyond that distance, the X ray and gamma radiation still sterilize exposed surfaces across hundreds of light years. To survive a supernova, you don't just need distance, you need an almost incomprehensible amount of it. If supernovae represent death on a cosmic scale, magnetars are what gets left behind when that death goes wrong. A magnetar is a neutron star with a magnetic field so extreme, it defies every intuition we have about physical limits. We're talking about fields a trillion times stronger than anything Earth's surface will ever experience. At a distance of 1,000 kilometers, that field would erase the iron from your blood before you even registered the danger. These objects don't need to explode to kill you, they simply exist, and that's enough. Every so often, a magnetar releases what scientists call a starquake, a sudden fracture in its rigid crust that unleashes more energy than our sun produces across 100,000 years. That burst travels outward at the speed of light, stripping electrons from atoms across entire star systems. One such event in 2004 was detected from 50,000 light years away and still measurably disturbed Earth's upper atmosphere. Nothing else in the known universe delivers that kind of violence from that kind of distance. 26,000 light years away at the very heart of our galaxy, something monstrous sits waiting in the dark. Sagittarius A star is a supermassive black hole with the mass of 4 million suns compressed into a single point of no return. The space surrounding it is not empty. It is a battlefield of radiation, shock waves, and colliding stellar winds. Stars orbit the black hole so fast that some complete a full revolution in just a few years, not millennia. The gravitational tidal forces near the center are strong enough to stretch and shred any object that drifts too close to the edge. Massive star clusters pump out ultraviolet radiation and X-rays in quantities that would sterilize entire solar systems without a second thought. Supernovae detonate here at a rate far higher than anywhere else in the Milky Way's quieter outer arms. Even the magnetic fields near the galactic center are twisted into violent, churning structures that accelerate particles to near light speed. This is not a place that occasionally becomes dangerous. It is permanently, relentlessly, catastrophically hostile to everything. Some black holes don't just sit quietly at the center of a galaxy. They feed, and when they do, the results are catastrophic on a galactic scale. These are called active galactic nuclei, and the most extreme version is something called a quasar. A quasar forms when a supermassive black hole pulls in enormous amounts of gas and dust, heating that material to temperatures that dwarf anything a star could produce. The energy released in that process can outshine every single star in the entire galaxy combined. Jets of radiation and plasma get launched outward at nearly the speed of light, punching through space for millions of light years in every direction. Any star system caught in the path of one of those jets would be stripped of its atmosphere, its chemistry, its ability to support life within moments. What makes this especially unsettling is that the destruction isn't local. A single feeding black hole can sterilize an entire galaxy from its very center outward. Somewhere in the observable universe, roughly once per day, a star dies in the most violent way imaginable. In a fraction of a second, a gamma ray burst releases more energy than our sun will produce across its entire 10 billion year lifetime. These aren't slow, quiet deaths. They're detonations that briefly outshine entire galaxies containing hundreds of billions of stars. The burst itself lasts anywhere from milliseconds to several minutes, but the damage it delivers travels outward at the speed of light. If one of these events fired in our direction from within a few thousand light years, the gamma radiation would strip away Earth's ozone layer almost instantly. This is not a place that occasionally becomes dangerous. It is permanently, relentlessly, catastrophically hostile to everything. Scientists believe a gamma ray burst may have triggered one of Earth's mass extinctions roughly 450 million years ago. To survive one safely, a planet needs to sit far from the galactic, Plane, away from dense star-forming regions where massive stars live and die fast. Distance is the only real protection the universe offers here. Now imagine compressing hundreds of thousands of stars into a space just a few hundred light years across. That's a globular cluster. And the density alone makes it one of the most persistently dangerous environments in the known universe. Stars in these clusters don't drift quietly past each other the way they do in open space. They interact, they pull, and they collide with a frequency that would be unthinkable anywhere else in the galaxy. Gravitational encounters constantly fling stars onto chaotic new orbits, destabilizing any planetary systems that might be trying to form nearby. And at the core of most globular clusters sits a dense concentration of neutron stars and black holes, the leftover wreckage of massive stellar deaths. Anything venturing too close to that core faces tidal forces, radiation bursts, and near constant gravitational disruption. What makes globular clusters uniquely deadly isn't one single catastrophic event. It's the relentless accumulation of danger from every direction, all at once, with no relief in sight. Two galaxies heading toward each other sounds like the ultimate catastrophe, but the reality is far stranger than a simple crash. Because galaxies are mostly empty space, the stars inside them almost never actually collide during a merger. What does happen, though, reshapes everything on a scale that's almost impossible to comprehend. Gravitational forces tear apart spiral arms and fling stars into wild new orbits across the combined system. Gas clouds slam together at enormous velocities, triggering violent bursts of star formation across billions of cubic light years. Those new stars burn hot and die fast, flooding surrounding space with radiation and shockwaves. Any planetary system caught inside one of those stellar nurseries faces a relentless barrage of ultraviolet light and supernovae. Meanwhile, the supermassive black holes at the center of each galaxy spiral inward toward each other over millions of years. When they finally merge, the energy released dwarfs almost anything else the universe can produce. A galactic collision doesn't kill you in an instant. It dismantles the conditions for life slowly and completely. Two neutron stars locked in orbit around each other represent something almost incomprehensible in scale and violence. Each one packs more mass than our sun into a sphere roughly the size of a city. The gravitational forces between them are so extreme that space itself warps and twists with every passing second. As they spiral closer together, they bleed energy by radiating gravitational waves outward across the cosmos. That in spiral can last millions of years, but the ending arrives without any warning at all. When they finally collide, the merger releases more energy in milliseconds than our sun will produce across its entire lifetime. The explosion is called a kilonova, and it floods surrounding space with lethal gamma radiation in every direction simultaneously. Heavy elements like gold and platinum are forged in that instant and scattered violently across light years of space. Nothing within a safe distance survives that detonation. Not planets, not moons, not any chemistry that life depends on. A stellar black hole doesn't announce itself with fire or noise. It simply pulls. The first thing that would kill you isn't the black hole itself, but the tidal forces stretching your body along the gravitational gradient. Physicists call this process spaghettification, and the name is almost too playful for what it actually describes. Your feet, closer to the singularity, would accelerate faster than your head, and the difference in pull would tear you apart at the molecular level. But even before that, the accretion disk surrounding the black hole bathes everything nearby in lethal X-ray and gamma radiation. That radiation alone would cook you long before tidal forces had their turn. And then there's time itself. Near the event horizon, time slows measurably relative to the outside universe. You wouldn't feel it, but an observer watching from a safe distance would see you freeze, redden, and fade like a dying ember. The event horizon isn't a wall or a surface you could even detect crossing. It's just the last address you'll ever have. If every danger we've covered so far is a loaded weapon, the core of a quasar is an entire arsenal firing at once. At the heart of an active quasar sits a supermassive black hole, sometimes billions of times the mass of our sun. It doesn't just pull matter in, it shreds it, heats it, and blasts the leftovers outward at nearly the speed of light. The accretion disk surrounding that black hole reaches temperatures of trillions of degrees, radiating more energy than entire galaxies combined. Jets of plasma punch outward for millions of light years in every direction, sterilizing anything caught in their path. Radiation at those distances would still be lethal, and you're not at a safe distance here. You're at the source. No magnetic field, no atmosphere, no distance offers any protection inside that environment. Every force that makes the universe deadly converges in one single screaming point. That is why the quasar core wins. Not because it's the biggest, but because it combines every extreme at once. Everything we've discussed so far, magnetars, quasars, the galactic center, they all exist within the same universe, playing by the same rules of physics. But what if the rules themselves broke down entirely? Two theoretical events sit at the absolute top of any cosmic danger hierarchy. The first is vacuum decay, where a quantum instability in the fabric of space triggers a bubble of destruction expanding at the speed of light. There would be no warning, no escape, and no physical process capable of surviving contact with that boundary. The second is the Big Rip, where dark energy accelerates so violently that it tears apart galaxies, then solar systems, then atoms themselves. Both scenarios don't just destroy life or planets, they erase the conditions that allow anything to exist at all. Every danger we've explored before this moment would become completely irrelevant in an instant. The universe isn't just capable of killing you. Under the right conditions, it can unmake the very stage you're standing on. After everything we've covered, Earth looks almost absurdly lucky. We orbit a calm, middle-aged star, far from the galactic center's chaos, nowhere near a magnetar or a collapsing stellar nursery. On the cosmic scale of danger, we live in one of the quietest neighborhoods the universe has to offer. But that doesn't mean we're untouchable. The most realistic threat to Earth isn't vacuum decay or a rogue black hole swallowing us whole. It's a gamma ray burst from a massive dying star within a few thousand light years, aimed directly at us. That single event could strip away the ozone layer and sterilize the surface within seconds. No warning, no preparation, no survival. The good news is the odds remain vanishingly small on any human timescale. What the universe has shown us, though, is that safety is never permanent. It's just a matter of where you are and how much time has passed.